Okay, so let me just fix this. All right, so this is the second lecture of the series. And today I would like to talk about examples of four-manifolds and constructions. I will only pick a few examples and a few constructions, which will be useful later on when we would like to find exotic smooth structures on four-manifolds. So the first and most important example, of course, is CP2, where I always imagine that we have three homogeneous coordinates. And so this is a complex manifold. As always, complex manifolds come with a natural orientation. So when you see this symbol, I always mean this equipped with the natural orientation. And CP2 with the bar on top is the same as is CP2 with the opposite orientation. Another fantastic source of four manifolds is, of course, taking lower dimensional manifolds and take their products. So products. So we can take, say, two-dimensional spheres, S2 cross S2. This is simply connected. Or a genus G surface and the product with the genus H surface. This is simply connected only if G and H are both equal to 0. So in this case, so these are when we take two-dimensional manifolds and they take their product. We can take S1 cross Y, so a one-dimensional manifold cross a three-dimensional one. This will never be simply connected. And indeed, this has two variations. We can consider S1 bundles over three manifolds, or three manifold bundles over S1. So we can consider Y, X, S1. Such a construction can be captured by one single map. This can be captured by a map from Y to Y. And the way you should think about it is that you take the interval cross Y, and then you take the two copies of Y over the two endpoints of the interval, and then you glue them together. And this map is called the monodromy of this fibration. So we get a fibration over S1 where the fibers are all these three manifold Y. Okay, so these give us plenty of four manifolds. Most of them are non-simply connected. This is simply connected. CP2 and CP2 bar are, of course, simply connected. Well, this, let me just give you an exercise. Sorry, so there was one other thing I wanted to say here, is that, of course, we can generalize this fibration construction here, and we can consider four manifolds made out of two surfaces where this is a surface bundle over a surface. And this is a much richer class than the product. I will not go into the details, but let me just mention that over S2, there are two S2 bundles. Well, there is the trivial one, and there is one other. And here is the first very simple exercise. Let's call it homework. Show that there is an S2 bundle structure over S2 on this connected sum. So we take CP2 and we take connected sum with CP2 bar. This is not S2 cross S2. We will get to there a little later and show that it also admits an S2 bundle structure over S2. Okay. Very good. So there are these fibration structures. We can make it a little more general by allowing fibrations where some of the fibers are singular. So let me just elaborate on these kind of examples, and I will start with a simple special case. So suppose that C1, C0 and C1 are cubic curves on the projective plane, i.e. they are given by zero sets of homogeneous cubic polynomials. So if you want a typical example of P0, x, y, z is something like x cubed plus y cubed plus z cubed. And then we take the zero set. This will be a complex one-dimensional object. It's not very hard to see that topologically such an object, if it is a smooth submanifold, then it will be a torus. And so consider, assume that C0 and C1 intersect transversely in 9 points. This 9 is somehow dictated by the fact that they are both cubic curves, so degree 3, they represent the 3 times the generator in the homology of CP2. So assume that and consider the following family, CT of T0, P0 plus T1, P1 equals 0, where T is an element in CP1. So is that clear? This is a family of cubic polynomials parametrized by the points in CP1. Clearly, if P0 and P1 are 0 at the same time, so we are talking about intersection points, then all these polynomials are 0 at those points. Outside of those 9 points, there is a single solution of the equation, of this equation. So you fix a point, then there is a single solution for T0 and T1. Let me just elaborate on that a little more. So suppose that the 9 points in C0 intersection C1 are P1 up to P9, then all the PIs are in CT and otherwise, and CP2 minus these 9 points are uniquely covered by this family CT, by which I mean that on every point in this complement, there is a single T for which CT passes through that point. So the usual picture, if this theta is symbolizing CP2, and this is C0, and this is C1, and forgive me that they don't intersect in 9 points, that would be too chaotic, but these are P1, P2, P3, and so on, then the other CTs are sort of passing through these points and never intersect each other and C1 and C0 in any other point. So they sort of one-sheeted cover the complement. So what can we do with that? Well, this doesn't look like a fibration. What we can do, so this gives a map from CP2 minus these 9 points to CP1. Namely, we associate the projective perimeter to a point corresponding to which the curve passes through. But it will not extend to CP2 because in these points you cannot determine, the point is sort of undetermined. We can do the following. We use the blow-up construction, and for that, I need a definition. So let's take B to be the following manifold. So we take pairs L and P, where these pairs in CP1 cross C2, and the condition is that P is in L. So remember for a split second, points of C2 are denoted by P. In CP1, this is just the space of lines in C2 passing through the origin. So I take those lines and those points, the pairs, where the point actually lies on the line. Okay, so this, it's not very hard to see. This is a 3 complex dimensional space. And we take those pairs which satisfy this relation. So this cuts down 1 dimension. Roughly speaking, this is a 4-dimensional manifold, a 2 complex dimensional manifold. Writing in coordinates, we have in homogeneous coordinates in CP1 and usual coordinates in C2, we have this relation can be formulated by the equation that U over V equals X over Y, which is sort of a little fuzzy when one of these numbers are 0. So I rather rewrite it as Uy equals Vx. And now you clearly see that we have a 3 complex dimensional space, and we just assume 1 complex equation, so we expect a 2 complex dimensional space as a result. Okay, so why is it relevant? Notice that this guy has 2 projections. As it is a subspace of a product, we can project down to CP1, and we can project down to C2. If you project down to CP1, taking the first coordinate, then the fiber will be all the points in that particular line. So that will be a C bundle, a complex line bundle. If you project down to C2, this is a trickier map because it's 1-to-1 away from the origin, right? If you pick a point which is not the origin, then there is a unique line which passes through the origin and this point. So that has a unique inverse image. But at the origin, every line passing through the origin passes through the origin. So there is a whole CP1. So what happens is that if you imagine C2 being such a flat thing, then this guy is also looks like a flat thing, except in this point, it has an entire CP1. If you do everything in the real, then you can recover the Möbius band from that perspective, and I encourage you to do that. It's a fun little exercise and not very difficult. But we can, so the point here is that if you take 2 lines passing through the origin and they intersect each other, when you go up to this picture, then they will pass through this extra CP1 in different points because they are coming from a different direction, and so they will become disjoint. So we can implement this picture around each and every such intersection point, and at the end of the day, this gives a fibration, and I put it in quotation mark, on the 9-fold blowup of CP2. this operation of replacing a little neighborhood of a point with this manifold B, with this guy, is called the blow-up procedure. And I hope you understand why. Somehow the point, the origin, will become an entire ball. So it's just like you blow air into that. Okay, so using the other description as a C bundle, in fact, we can see what happens with the blow-up. So can you close the window? I'm sorry. Topologically, a blow-up is just connect sum with CP2 bar. It's not very hard to see that this C bundle has Chern class plus or minus 1. And it needs a little bit of a suffering to actually see that the Chern number is -1. So really, it's a CP2 bar. And so at the end, we get a new manifold, which I denote by E1, which is just CP2. And we have the connected sum with 9 CP2 bars. And it comes now with a map to CP1. Now the map extends over these 9 points because we just blew them up. And the generic fiber will be a torus, will be a cubic curve. The question is whether all fibers are tori, and we can see that this is not possible. If all fibers are tori, for fibrations, the Euler characteristic is multiplicative. So the Euler characteristic would be the product of the base and the fiber, which is 0. That's a contradiction. So it cannot happen that all the fibers, all the curves in this family are smooth curves. There are certain singularities, and I will not go into the details. The singularities are classified by Kodaira from the 60s, and I will give you one example a little bit later on. Okay, so what can we do with these guys? Well, so I promise you examples and constructions. So here is the first construction. If we have two such objects, say we have two copies of E1, sorry, I have to turn the blackboard. If X1 and X2 both admit such a fibration, these are called elliptic fibrations, then we can do the following. Take one regular fiber, which looks like T2 in each, delete a tubular neighborhood of these two fibers, and glue together the results via a fiber preserving, orientation reversing DFO. So let me just draw. So we have X1. This comes with a fibration where the typical fiber is T2. And we have X2 with the same structure. Let's pick two regular fibers and take out their little neighborhood. As a fiber, T2 has trivial normal bundle. You can move around. So these boundaries will be both T3s. And we would like to have a diffeomorphism between the two boundaries, which keeps the fibrations, but reverses the orientation. In order to keep orientation when you glue, you have to use an orientation reversing diffeomorphism. So by doing that, we get X1 fiber sum X2. Sometimes the result might depend on what diffeomorphism you take. Usually we sort of pick a canonical one. We just take the complex conjugation on this S1 factor down here, and then you just take the two trivial fibrations together. So, of course, we have only one such example so far, but if we have one, we can already construct infinitely many. So we only have this E1. So let's take E2 to be E1, fiber sum E1, and then continue this procedure and define En as the fiber sum of En minus 1 with E1. So here is our homework assignment. Show that pi 1 of En is trivial. Compute the Euler characteristic and the signature, and show that the intersection form of En is even if and only if N is even. So by Friedman's theorem we had earlier on, these computations completely determine the four-manifold En up to homeomorphism. So we hope that among those we will find exotic four-manifold pairs, and this is exactly what will happen. Let me just elaborate a little bit on this E2. This guy is called the K3 surface, and it has a number of constructions, and I will not talk about those. Use this as a definition, and I will mention one more, also constructed as follows. So we take the four-dimensional torus. I didn't spell out this manifold because I forgot, but this looks like the simplest possible four-manifold. It is made out of four one-dimensional pieces. It's just S1 cross S1 cross S1 cross S1. But it turns out to be a rather complicated four-manifold from our perspective. For example, it's not known whether there are exotic copies of the four-dimensional torus. It has a large fundamental group, and then we just don't know any construction which reconstructs it as a topological manifold with a different smooth structure. But notice that there is an involution. You can take complex conjugation on each factor. So we can consider a Z2 factor. I'm not saying that you complex conjugate on the first one and don't do anything on the others. You just simultaneously conjugate on each factor when you imagine S1 sitting in C. And it has 16 fixed points. Obviously, complex conjugation has two fixed points, so 2 times 2 times 2 times 2 fixed points. Well, in those points, the result is not a manifold. So we do the following. So near a fixed point, the manifold looks like a cone on S3 over Z2, which is just RP3. So the singularities are cones on RP3. So what we can do, we just cut out this cone and reglue, delete those, and reglue the unit disk bundle in the cotangent space of S2. It needs a little bit of a thinking that this is also now a smooth manifold with RP3 as boundary. And so what the pictorial image should be something like this. There are these 16 singularities. I only draw 3, but you can imagine that there are 16 of these cusps. And then you just cut it out and you glue in the unit disk bundle of the cotangent bundle of S2. And you do it for all of them, and so on and so forth. And the claim is that the result is the K3 surface again. So this will be diffeomorphic to my E2 from earlier on. And you should see these -2 spheres in the unit cotangent bundle of S2. So every description of the K3 shows a different topological characteristics. For example, this one shows the existence of these spheres. Okay, so another family of 4 manifolds can be defined as follows. Now we move on, and we'll take submanifolds in CP3. And for that, I need my sheet. So SD is defined by the following equation. So we take homogeneous coordinates in CP3, and we take homogeneous degree D equations. For example, I just take Zi to the D, where I goes from 0 to 3. It needs a little bit of a thinking that what we get is a smooth submanifold of complex dimension 2, real dimension 4. Here is a little proposition. So we can compute the second Chern class of this manifold. And if we evaluate it on the fundamental class, needless to say, as a complex manifold is again oriented, then we get the following formula. So it's D squared minus 4D plus 6 times D. Remember that this is just the Euler characteristic, which in this case will be just 2 plus the second Betti number, since pi 1 of SD is trivial. C1 squared, the other 4-dimensional characteristic class, is given by 4 minus D squared times D. And the class C1 is divisible by 2 if and only if D is even. And now it's again an exercise to show that from these data, one has to be able to determine the homeomorphism type of these SDs, because C2 and C1 squared determines the Euler characteristic and the signature. So by Friedman's theorem, we know the topology. And so let me just give you before, it's like a homework prime. If you have better things to do, don't do that. But if you would like to understand how these things work, then please verify these claims in the proposition. These 3 are typical and not very complicated massaging of characteristic classes. Simple connectivity is much more complicated. It relies on a Lefschetz hyperplane theorem. So this is the hard part. Notice that in the previous EN definition, the simple connectivity is sort of easy, but here this is a little more challenging. And let me just tell you the end result. What are the intersection forms of these guys? And these will be very long formulas, so I have to copy. So Q of SD is lambda D times 1 plus mu d minus 1. So it's a diagonal matrix with lambda d copies of 1 in the diagonal and mu d copies of minus 1 if d is odd. And I will tell you what lambda and mu are. And LD times minus the E8 lattice plus MD times this age. Remember, this is just the hyperbolic pair when d is even. And I will just tell you what lambda d is. It's 1/3 d cubed minus 6d squared plus 11d minus 3. Mu d is 1/3 d minus 1, 2d squared minus 4d plus 3. LD is 1/24 d times d squared minus 4, and MD is the same as mu d. So from this, we have an infinite family of manifolds. Again, we understand their topology fairly well because of Friedman's theorem. The intersection form characterizes them. And we hope we will find some other manifolds which have the same intersection form. So they are homeomorphic, but we will develop a method to show that they are not diffeomorphic. So this is like a not very long-term plan. Let me spend a little more time with complex surfaces. Let's switch back to the board. Yes. Okay. So suppose that X is a complex surface. As you saw so far, they provide the richest source of smooth four manifolds. Somehow, all the ENs, all these SDs are complex surfaces, so it makes perfect sense to sort of better understand how they are positioned and how can we classify them. And then I will tell you some constructions which are not complex anymore and give you examples of non-complex surfaces. But so the first thing we can do with a complex surface, we can take the determinant line bundle of the cotangent bundle of X. So remember, this is, sorry, C is here. So this is a complex two-dimensional bundle, and we take the complex determinant. So this is a complex line bundle. And let's take Ln to be the n-fold tensor product of this bundle. So this is still a complex bundle. And then we can take H0, I don't know what happened with this chart, H0 of Ln, this is just complex, holomorphic sections of Ln. Now, we know that if we have a bundle and we take all the C0, C infinity sections, we get typically an infinite dimensional. If X is a complex compact surface, then these holomorphic vector spaces tend to be finite dimensional, as it is in this case, finite dimensional vector space. And we can do the following. So we define a map from X, which might not be defined everywhere, into the projectivization of this space by the following recipe. So fix a basis sigma n of this space of sections, and then send X, so a point from my complex surface to here. Notice that the individual terms do not make sense. They live in a bundle, right? So these are not complex numbers, but they are in a complex line bundle. So the ratio does make sense. So it will be an element here. And now we do the following. So we define kappa of x, the Kodaira dimension of x, just as the maximum for n, the dimension of, let's give this map a name, I call it phi n. This n is the same, right? So whichever line bundle we use, and we just take the dimension of the image of phi n. So we start with a two complex dimensional object, x, and then we take its image. This can be, what can it be? It can be two-dimensional, it can be one-dimensional, it can be zero-dimensional, or it can be the empty set. It can happen that, you know, this map is not defined everywhere, because if we take the common zeros of sigma 1 up to sigma n, then this object is not defined. So it could happen that, for example, this space is the zero-dimensional space, and then it's not defined anywhere. So we assume that this is an element of this set, where for convenience, the dimension of the empty set is denoted by minus infinity. Okay? This is when the image is a point. This is when the image is a curve, a complex curve. And it's sort of an embedding. It doesn't have to be an embedding. It can contract some parts, but the image is also a complex surface. Okay, and so here is the theorem. Let's call it a scheme, classification scheme. So if kappa is minus infinity, then X is an S2 bundle or CP1 bundle over a curve plus some other examples. But if we assume that it has to be a Kähler manifold, so it has to admit a symplectic structure, then this is the only possibility. These other examples are not so well understood from the complex point of view, but there are examples. For example, S1 cross S3 is such an example. I will give you a complex structure on that a little later on. If kappa is equal to 0, then we have a complete understanding, and these are the four-dimensional torus, K3 surface, T2 bundles, and that's it. If kappa is 1, then as examples we have, or old friends, or not so old friends, these elliptic surfaces, and there are some variations of these elliptic surfaces. Why do we call them elliptic surfaces? Because the fibers are tori, which have the name of an elliptic curve. So these guys are families of elliptic curves, and this is why they got the name elliptic surfaces. And finally, if kappa is equal to 2, then those surfaces are called general type. And examples of surfaces of general type are, for example, these guys SD, where D is at least 5. I didn't mention because I forgot, but S1 is, of course, just CP2, and S4 is yet another appearance of the K3 surface. I will not prove that at all, but I just mentioned that, you know, for a while, these are easy to understand. And then starting at 5, they become these general type surfaces. So, you know, the way you should understand the classification scheme is that for small kappa, we have many examples and a good understanding. And when kappa is 2, then all hell breaks loose. And we just, it appears here. Yes, so, well, the K3 is here and not there. But it's a very, this is the only elliptic surface. Of course, I mean, E1 also appears here, and this is also not an elliptic surface. It's a blow-up of CP2. Yeah, because I forgot to mention that, of course, CP2 is here. Yeah, so the way you should understand that, I take larger and larger classes, and if a guy would belong to a previous one, then it does belong to the previous one. Let me mention one theorem, which is sort of brings a little bit of an order into this picture. Fact, if C1 squared and C2 are fixed, then there are only finitely many diffeomorphism types of complex surfaces of general type with the given C1 squared and C2. So although it looks like a chaos, but up to homeomorphism, you know, when C1 squared and C2 sort of pin down the homeomorphism type, of course, only if the surface is simply connected, and these are not always connected, but there is some kind of an order. Once you've picked the characteristic numbers, and you know that you are working with a complex surface of general type, there are only finitely many. For some pairs, we do know the exact number of these finitely many, but for most, we don't. Okay, so now I would like to tell you a few constructions. So let's start with this board. Constructions. So the first construction is called the Glock twist. And it goes as follows. So suppose there is a sphere in my 4-dimensional manifold. It's an embedded sphere. With trivial normal bundle. So the tubular neighborhood of that sphere, which I will call S from now on, is just S2 cross D2. So again, I will try my little picture. This is X, this is the 4-manifold, this is my sphere, and I take a tubular neighborhood, and this is S2 cross D2. Well, the boundary of this tubular neighborhood is S1 cross S2, right? It's S2 cross the boundary of this guy. And there is a strange diffeomorphism of this S1 cross S2. So imagine S1 cross S2 by taking a sphere and just move around the circle. Of course, in the 3-dimensional space, it's not embedded, but you can imagine that. And now I will define a diffeomorphism by saying that when I move to angle theta in S1, then I apply a rotation of S2 by angle theta. Right? There is a north pole and a south pole, they never move. And then as I go around, then they turn more and more. And when I come back, then you just come back. Okay, so this is my S1. There are these S2s over the points. And at angle theta, you apply a rotation of angle theta. So this will be a diffeomorphism from S1 cross S1 to its self-diffeomorphism. And so take out and then glue back the same S2 cross D2, but now apply this diffeomorphism. So X minus nu of S, and glue back S2 cross D2 with this, you know, I denote it by R because it comes from a family of rotations. And this is what we call XS, the Glock twist along S. No manifold is known where this changes the topology, the differential topology of the manifold, but potentially it can. I didn't turn the, sorry. So I was a little sloppy and I didn't turn the black. So now here is the board. Let me wait a few seconds and you can absorb it. I'm sorry. Okay, so well, this is one construction, and what's next? The power of this construction is that it doesn't need very rich topology from X. You just have to find an embedded S2. For example, if X happens to be the force sphere, you can find interesting knotted S2s in S4, and you have a hope that you will get, at the end of the day, an exotic structure on S4. Needless to say, nobody managed to do that until now, because it's still an open question whether S4 admits an exotic differentiable structure or not. This is the only standing case of the family of Poincare conjectures. It is typically called the four-dimensional Poincare conjecture. Four-dimensional smooth Poincare conjecture. Okay, so this is one construction. Let me give you another one. Now I hope it's visible what I'm writing. So the next one is requires a little more topology. So suppose X is a smooth 4 manifold, as always. And now we have a torus inside T, inside X, two-dimensional torus with trivial normal bundle. So the tubular neighborhood is just D2 cross T2, very similar to the previous case. And now we do the following. So cut this out. No, don't cut out. Take this and construct the following object. So consider a knot K in S3 and let MK be zero surgery on this knot. So this is a three-dimensional manifold, and consider S1 cross MK. Now this is a four-dimensional manifold which has a nicely embedded torus inside, since let MK be the meridian of K in S3, and then take S1 cross MK as a torus inside this 4-manifold. This is also a torus with trivial normal bundle. So we can apply our previous trick, what I explained for the fiber sum. You have 2 manifolds, you have 1 torus in each, which has trivial normal bundle. We take out the neighborhoods and we glue together the complements. So we just take X minus the neighborhood of T union this S1 cross MK minus S1 cross MK along this T3. Once again, we have to be a little bit careful of how to glue the 2 manifolds as before, but in the situations we will use, I will explain exactly what kind of gluing we would like to take. The result will be XK. So the name of the game is that we start with a 4-manifold and the torus inside and the knot in S3, and we create a new 4-manifold XK. We will later on assume specialties about this embedding, and then it will be not so hard to see that X and XK will be homeomorphic, again, invoking Friedman's theorem. Notice that you can immediately show that the characteristic and the signature doesn't change. We have to worry a little bit about the fundamental group. So we'll assume that X is simply connected and T is specially embedded. Then XK will be simply connected. Then they will be homeomorphic. And I will quote a theorem saying that for many Ks, they will be different as smooth manifolds. So in the last couple of minutes, I would like to finish with one more construction. This is the rational blowdown. Construction. And it goes as follows. So we consider the family of graphs which contains of linear framed graphs, where framing of a graph means that we attach an integer to every vertex, which contain this very simple guy, a graph which has only one vertex, no edges, and the -4. And if gamma linear graph is in G, then the one which we just stick -2 to the left end. And if it was A, then we replace it with A -1 on the other end, is also in G. So this is a construction. Notice for -4, this gives us that -2, -5 should be there. And then for this one, we have 2 options. We can put the -2 on one end, and then it will become a -6. Or I reverse the order of -5 and -2, and we get -2, -5, -3, when I view this previous graph like this. And then we can go on and make larger and larger graphs. Okay, so G is the family of these graphs. And now suppose that X is a smooth 4-manifold which contains C1, Ck embedded spheres intersecting each other according to some gamma which is from G. So again, this is my X, this is X C1, C2, C3, and so on, Ck. They intersect one after the other because the graph is a linear graph, and the self-intersections of these spheres are dictated by the framings of the graph. So suppose we have that. And then we will do the previous trick, or a variation of the previous trick. So this is my C1, C2, C3, Ck. I take a tubular neighborhood of this configuration, and I consider the complement, let's C to be the union of these curves. And I will glue in a four-manifold B, which has B is a four-manifold with boundary such that the rational homology of B is the same as the rational homology of the disk, which just says that it's a Q in degree 0, and otherwise it is 0. We know how to compute the homology of D. And this is what I will call X gamma. Notice what happens. We have lots of curves here, lots of two-dimensional submanifolds, and suddenly I take them out and replace with something which has no rational homology. So this is why it's called a rational blowdown operation. We just, up to rational homology, we just got rid of these guys. We just blew them down. They just collapsed. But at the end, we get a smooth manifold. Of course, the question is, why does this B exist? And this is where the assumption of having gamma from this special family G comes in. Typically, such a B just doesn't exist. But in this case, it does. So let me give you an argument for that. And this will be the conclusion of today's lecture. So let's start with -4. So clearly, this is the boundary of such a B, because we can take CP2, we reverse the orientation, we take the degree 2 curve, which is a sphere, which can be given by two lines intersecting in one point, and then you smooth that point. And this has self-intersection 4 in CP2, so has self-intersection -4 in CP2 bar in the reverse orientation. And so let's take the tubular neighborhood of this guy and consider the complement. The complement doesn't have any homology, rational homology, because the generator of CP2 somehow picked up all the homology, so there is not much left. So for this guy, we are done. Let's do one more step. So we take our -4 sphere, and we can take a generator of the second homology, which is a -1 sphere. So it's -4, -1. They intersect in 2 points. If we take the origin orientation and then we reverse, these will be negative intersections. So we just take this guy with the reverse orientation. So we have 2 positive intersection points. And then we just take one and blow it up. So this will be in CP2 bar, connected some CP2 bar. And now I will have this -4. It's connected to -2. And then there is the blow up gives you a -1 sphere. That's the exceptional divisor, the 0 section of that line bundle. Sorry, that's not mine, that's -5, right? We just change the normal bundle of this guy and also of that guy. So you see the -5, -2, and now you sort of see how this procedure of continuing to construct the chain follows, because now we can take these 2 points and we can take which one to blow up, and then we just keep doing that procedure. And once again, this is in here, the second homology is 2-dimensional in this 4-manifold, and we take out -5 and -2, 2-dimensional many second homology elements. What's left over, so in the complement of these two curves, the complement of the tubular neighborhood of the union of these two curves has exactly the property. So I didn't go in very much details, but it's easy to complete this argument, and then you can convince yourself that such a B does exist if your graph comes from that construction, is in G, and then this operation can be carried out. So we have now lots of examples, lots of constructions. We do have Friedman's theorem, which tells us when do we have homeomorphisms between four manifolds, or in some cases it guarantees a homeomorphism. All we need to produce exotic pairs is to develop an invariant which distinguishes smooth structures. So guess what will we do next time? I will give you a very quick introduction to the Seiberg-Witten invariants, which exactly do. And then we will come back to these examples and cherry pick the ones which give us examples of homeomorphic, non-diffeomorphic manifolds. So that's the plan. Okay.